So I'm going to talk about the second law of thermodynamics, which is chapter 6 in our book. So now, for a process to occur, it does not have to violate the first nor the second law of thermodynamics. The first law of thermodynamics states that energy is not created or destroyed. Energy is only converted and transferred to other forms. And in this case, the second law of thermodynamics, it's about the direction and and that energy has not only quantity but quality. So it is used for determining the theoretical limits for the processes of engineering and also the degree of completion of these chemical reactions. So now in this chapter we're going to have this diagram in which we have a thermal energy source that is supplying heat and a thermal energy sink which is absorbing heat. So in this diagram, the thermal energy source, it's called the thermal energy reservoir, and the reservoir is a large thermal energy capacity, has a large energy thermal capacity that can supply or absorb thin amounts of heat without any change in temperature. And so we're going to have this one. And because we cannot convert heat into work as such, we have to use devices such as heat engines. So in this chapter we're going to work with heat engines, and the most common one is a steam power plant. And now we have this diagram, this one, and we have the source that it has a higher temperature because the heat is transferred from the higher temperature to the lower temperature. So we have a source that it has a higher temperature that it's supplying heat, and in order to produce this heat into work, we have the heat engine that it's producing work as such. But in these diagrams we're going to have also heat that is not produced to work, and this heat goes into a sink, which is commonly the air or large bodies of water, for example. And this work that is going out, the work net, is the work out minus the work in the heat engine. And the work that is going out also states that it's the heat that is going in minus the heat that is going out, and this is this one. And we're going to work with thermal efficiency because as I said it before, some heat it's not transferred into work, so only parts of the heat is converted. So it is due because in order to complete the cycle, this heat must go out. So Kelvin Planck states that the thermal efficiencies of work-producing devices are relatively low. And today, most devices convert almost 1/2 of the heat into work, so it is a very low efficiency, but it is due because many reasons, as we will discuss later. And to calculate the thermal efficiency of these devices, it is stated with this formula: equals the work out over the heat that is going into the heat engine, and this translates into 1 minus Q out over Q in. And it is important to state for me as an IDS because almost 1/2 of the energy supplied it's not converted into work. It ends always as waste energy or useless energy that causes a lot of consequences. For example, and now engineers are trying to design devices that has a higher efficiencies, because a higher efficiency equals a less, for example, fuel consumption, and fuel consumption equals lower fuel bills and lower contamination and pollution. So now we have these types that are called refrigerators and heat pumps. So we can see that it's the same diagram, only that refrigerators cause the reverse effect. So in these types of systems, we want to transfer from a low temperature to a high temperature, but because this violates the laws of thermodynamics, we have to use a device such as refrigerators. And the most common refrigerators are the vapor compressor refrigeration cycle, and this cycle works as such. The refrigerant enters the compressor as vapor and is compressed to the condenser pressure, and then leaves at a higher temperature and cools down as it flows through the condenser by rejecting heat to its surroundings. And now in a tube, its temperature and pressure drops, and then enters the evaporator, absorbing heat from the refrigerated space. So if it absorbs heat, it cools down the space. So that's how the refrigerator works. And we can see that the direction is opposite to the other types of systems that we saw before. And now we saw that with the other types of systems we can calculate the thermal efficiency, but now we're not going to call it as a thermal efficiency, because in a refrigerator we can have that the amount of heat removed from the refrigerated space can be greater than the amount of work input, and thus the efficiency can be higher than 1. So we are then calling this efficiency the coefficient of performance, which equals the desired output over the required output, and this is the QL over the work out, and this work net that must over the work in, and this work net equals the heat transfer from the higher temperature over the heat transfer of the lower temperature. And we can translate these coefficients of performance as this formula. And now other types of systems are the heat pumps. The heat pumps want to maintain, if we had a heat pump, that means that we want to maintain a space at a higher temperature. So the heat pump basically absorbs heat from a lower temperature source. So for example, in this case we have a warm house. So if we wanted to maintain the house warmer, we can put a heat pump, and the heat pump will absorb heat from the outside, which has a lower temperature. So the direction of the heat transfer goes as this. And to calculate the coefficient of performance, it can also be more than 1, and it equals the desired output over the required input, and this translates to QH over the work that it's going in, and this translates into this, and the coefficients of the heat pumps will be equal to the coefficient of performance of the refrigerator plus 1. This is a formula that we can apply, and as a fact, most heat pumps that we have today the coefficient of performance goes from 2 to 3. This is the average cup. So now, I mentioned the Kelvin-Planck statement, and another statement that we have to take into account is the Clausius statement that says that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So we cannot operate unless its compressor is driven by an external power source, such as an electric motor. We have seen it before. So any device that violates a Kelvin-Planck statement also violates this Clausius statement, and vice versa. And the devices that violates in both of them are called the perpetual motion machines. And now, a process is on a certain direction, but there are processes, but if the process goes in the direction and can go back into the initial state, is called a reversible process, and the reversible process only goes into one direction and cannot go back into the initial state. In this case, in thermodynamics, the reversible processes are the ones that does not act and leave any change in the surroundings, and the irreversible processes are the ones that usually do some change in the surroundings, and therefore they cannot go back into the initial state without change this in the surroundings. So a thing we must take into account is that the reversible processes does not occur in nature, but we use them because it is easier to analyze them, and also it serves us an idealized models, because the more close the processes are, the processes in, if the process is more close to the reversible state, it has a higher work delivered by a work producing device, or a less work required by a work consuming device. And this is very important for the engineering processes. So there are some things that cause a process to be irreversible, and these are called irreversibilities, which are a friction, for example, which friction is a force that opposes the motion, the natural motion, and the unrestrained expansion of a gas, and heat transfer. And these cause a process not to be irreversible. So we can have an internally and externally reversible process. The internal reversible is that when no irreversibilities occur inside the process within the boundaries, and the externally irreversible is when no irreversibilities occur in the surroundings, in the external of the boundaries. And one type of internal reversible is the quasi-equilibrium processes. So now, a reversible, the more known and used reversible process is the Carnot cycle. This cycle is this one. So this cycle has 4 steps. One is the reversible isothermal expansion, the reversible adiabatic expansion, the reversible isothermal compression, and the reversible adiabatic compression. And these are the 4 steps. So in step 1, we have that an energy source is transferred into the gas. So the gas will expand, and when the gas expands, the temperature drops. So some heat is transferred to the surroundings, and that's step 1. So for the step 2, which is called the reversible adiabatic expansion. TH goes to TL, and for part 3, which is a reversible isothermal conversion, as the gas is compressed, its temperature tends to rise, but as soon as it rises by an infinitesimal amount dt, heat is transferred from the gas to the sink, causing the temperature to drop to TL. And for the final step, the low temperature reservoir is removed, so the gas returns to the initial state, and this is a Carnot cycle. The Carnot cycle has principles which are called the Carnot principles. There are two. The first one is that the efficiency of a reversible heat engine is always lower than the efficiency of a reversible engine operating between the same two reservoirs. And the second one is that efficiencies of a reversible heat engines operating between the same two reservoirs are the same. So this translates into no heat engine can be more efficient than a reversible heat engine that it's operating between the same reservoirs. And these are the Carnot principles. We have the thermodynamic temperature scale, which is a temperature that is independent of the properties of the substance. And since the energy reservoirs are characterized by their temperatures, the thermal efficiency of reversible heat engines can be a function by their temperatures only. So we can have this formula, that is the efficiency of the reversible processes, equals this. And this offers a great conveniences in thermodynamic calculations because we are only working in terms of temperature, and this translates into this formula. So now the Carnot cycle device is called the Carnot heat engine, and it is the best known, as I already said, the best known reversible engine. And to calculate the efficiency, it's this formula, which is 1 minus QL over QH. Because it's lower than 1, it's called an efficiency. And QH is the heat transfer to the heat engine from a high temperature reservoir to at higher temperature, and QL is the heat rejected to a low temperature. And this is the highest efficiency a heat engine operating between the two thermal energy can have. And now that I have already said this, we have to consider that most engines, heat engines that we have today, that work with almost 40% of efficiency, which can be lower than, like really lower than the 100, but we have to take into account that we cannot compare these efficiencies to 100. We have to compare it to the efficiency of a reversible heat engine operating between the same temperature limits, because this is a true theoretical limit for this efficiency, not the 100%. And we also have to take into account the quality of energy. This is the second law of thermodynamics, that it states that the energy does not only have quantity, but it has quality, because in energy we are looking for the higher efficiencies that cause us lower money. So in order to produce work, we can have heat and energy. And energy is more valuable than heat because 100% work can be transferred to heat, but only a small fraction of heat can be transformed to work. So this is very important for engineering processes. And last, we have the Carnot refrigerator and heat pump, and these cycles are the opposite of the Carnot cycle, and this the coefficient of performance can be calculated with this formula, and the coefficients of performance of a reversible refrigerator or heat pump is a maximum theoretical value for the specific temperature limits. So that's it for chapter 6.